We have a model with knobs, and we have a loss that scores how bad the model is. Now comes the only remaining question. How do you actually turn the knobs to make the loss smaller, without guessing, without magic, and without trying every possibility? Imagine trying to find the lowest point in a foggy landscape. You cannot see the whole terrain, only what happens right where you stand. Random wandering sometimes works, but it is slow and unreliable. We want a rule that uses local information to decide a direction that is guaranteed to reduce the loss, at least for a small step. In episode 2, we built a line. Prediction equals slope times x plus intercept. In episode 3, we built a loss, mean squared error. Put them together and the loss becomes a function of the parameters, slope and intercept. So training is not mysterious. It's just minimizing a function of two variables. Let's use a tiny dataset so we can see everything. The first point is exactly at the origin. We pick a bad initial line and we compute the loss. Then we slightly nudge the slope and intercept and watch how the loss changes. That change is the key. It tells us which direction is downhill. Here is the simplest possible idea for downhill. If increasing the slope makes the loss larger, then decrease the slope. If increasing the intercept makes the loss larger, then decrease the intercept. So we need two numbers, how sensitive the loss is to slope and how sensitive it is to intercept. Those are partial derivatives. For mean squared error with a line, we can compute the derivatives exactly. Each point contributes a residual, prediction minus truth. The derivative with respect to intercept is basically the average residual. The derivative with respect to slope is basically the average residual times x. So the update is push the line down where residuals are positive and pull it up where residuals are negative. Now watch training as pure geometry. Each step computes the slope of the loss with respect to the parameters, then takes a small step in the opposite direction. The blue line on the data plot updates and the residuals shrink. At the same time, a dot moves across the parameter plane, tracing a path toward the minimum. To make the landscape visible, lift the loss into a third dimension. Every pair of parameters becomes a height, the loss. This surface is a bowl, but not a perfectly round one. Gradient descent is like walking downhill on this surface. The path bends because the steepest direction changes as you move. The step size matters. If the step is too small, you crawl. If it is too large, you can overshoot and bounce around, sometimes even diverging. The same gradient can be safe with one step size and disastrous with another. This is not theory. You can see it as the path either spirals into the minimum or ricochets across the bowl. Now, we do the full training run on the data, and we enforce a strict checkpoint. The final line must match the exact ordinary least squares solution for these points. That means we compute the true best slope and intercept, and we show gradient descent converging to that target, not approximately, but exactly to numerical tolerance. Here's the complete algorithm in plain code. No training framework, no optimizer class, just compute predictions, compute residuals, compute gradients, update parameters. Notice what makes this scalable. You never search the whole space. You only need local slope information, which you can compute from sums over data points. Digest the upgraded mental model. Loss is a height over parameter space. The gradient is the direction of steepest uphill, so negative gradient is steepest downhill. Gradient descent is just repeated small downhill steps. And for linear regression with squared loss, this downhill walk lands exactly on the same solution as ordinary least squares. Next episode, we break something on purpose. If you keep stepping downhill long enough, you can fit the training data extremely well, even when the data contains noise. So what exactly goes wrong when the loss keeps decreasing, but predictions get worse? That question forces us to invent the geometry of overfitting.